Hey everyone, welcome. Let's jump right into this explainer for OpSciEd Unit 6.5, all about natural hazards. Now, I know, spending weeks learning about massive earthly disasters, it can feel a bit overwhelming, right? Maybe even a little scary. But here's the absolute most important thing to remember as we review. Understanding the science behind these events, that is exactly what empowers us. It literally takes the unpredictable and makes it understandable, and that means we can stay prepared, stay safe, and protect our communities. So today, we're going to walk through exactly what you need to know for your upcoming assessments. We're breaking down the whole shebang, from the raw science of tsunamis to the nuts and bolts of engineering warning systems.
Because really, everything we've been studying, it all comes back to this one massive driving question. Where do natural hazards happen, and how do we prepare for them? This is the anchor for your entire unit. As we go through this explainer today, just keep this question floating in the back of your mind. If you can answer the where using real scientific data, and the how we prepare using solid engineering principles, well, you're going to absolutely crush your final assessments. So here's our roadmap for today. First up, the threat of tsunamis. Then, causes and global patterns. Third, detection and warning systems. And finally, preparing your local community.
All right, Section 1, the threat of tsunamis and acknowledging the impact on communities.
Let's dive right into that threat. I want you to think back to Lesson 1. We kicked off this unit by looking at a specific anchoring phenomenon, right? The 2011 earthquake and tsunami in Japan. We watched videos, read texts, and honestly, it carried a lot of emotional weight. But we didn't do that just to stare at the destruction. We did it to ground our scientific inquiry in reality. Seeing what actually happens to a community when a tsunami hits, like the sheer speed of that water washing over massive seawalls. It's a devastating reminder of why hazard preparation saves lives. It is the why behind all the data and models we study. It shows us that mitigating these hazards, it isn't just some academic exercise. It's a critical, life-saving mission.
Moving on to Section 2, causes and global patterns, the science behind the surge. Now, let's shift gears from that emotional impact to the objective science behind the surge. We're looking at raw data here, mapping 100 years of historical tsunami events. And for your assessments, you really need to be able to look at large data sets just like this one and forecast future risk. So let's practice our what I see, what it means strategy right now. Take a moment. What do you see? Well, you'll see dots indicating earthquakes, volcanic eruptions, and landslides. But actually, more importantly, look at where those dots are located. They're not just randomly scattered all over the globe, are they?
When we really interpret that map, some distinct patterns jump right out. Historical tsunamis are heavily clustered in the Pacific Ocean basin, and they are highly correlated with earthquake zones. Now, sure, we occasionally see triggers from volcanoes or landslides, but the vast majority, they are tied directly to underwater earthquakes. And what this means for your assessment is this. We have clear historical evidence that natural hazards happen in predictable regions. Science assumes that events in natural systems follow consistent patterns. So, by identifying those patterns, we can predict exactly which communities are most at risk.
But, just knowing where they happen isn't quite enough. We've got to know how they happen, right? It's a huge cause and effect chain reaction. Step 1, the ocean floor literally snaps and breaks during an earthquake. Step 2, that massive release of energy transfers directly into the water, pushing it outward. Step 3, the wave moves rapidly away from the epicenter across the deep ocean. I mean, we're talking speeds as fast as a commercial jet plane. Crazy, right? But Step 4, this is the most critical one for coastal communities and definitely for your test. As that wave approaches the shore and the water gets shallower, the wave's amplitude, or height, increases drastically. That specific change in amplitude is exactly what turns a fast-moving deep-water wave into a devastating coastal hazard. Okay, Section 3. Detection and warning systems. These are the engineering solutions to protect communities.
So now that we know who's at risk and the science of how tsunamis actually form, what can we do to mitigate the effects? This is where we get to put on our engineering hats. To protect a community, engineers, they don't just build one single thing. They design a complex system made of interacting subsystems. First, detect. We need sensors out in the ocean to catch that energy transfer early on. Second, warn. Once it's detected, we need communication systems to rapidly alert the community. Remember those alarm sounds we listened to back in Lesson 7? That kind of thing. And third, reduce damage. This involves structural engineering to protect buildings and having crystal clear evacuation plans for people. All of these moving parts have to work together perfectly. Because think about it, if the detection works, but the warning fails, the entire system fails.
And that brings up a really key standard you covered back in Lesson 8 regarding that warning subsystem, specifically the difference between analog and digital signals. Look, when you're warning a community about a tsunami, your communication system has to be totally flawless. Analog signals, they're continuous waves, which makes them really prone to interference and degradation over long distances. Digital signals, on the other hand, are sent as discrete wave pulses. Think of it like this. Analog signals are kind of like an old walkie-talkie that gets super staticky the further away you walk. But digital signals, they're like a text message. They arrive exactly as they were typed, no matter the distance. That makes digitized signals a highly, highly reliable way to encode and transmit information. So for your assessment, just remember, digital technology is the go-to engineering solution for emergency communications because its reliability is just unmatched when lives are literally on the line.
Which brings us to Section 4, preparing your local community, applying all this global science to local safety. Finally, let's take everything we've learned about these huge global phenomena and apply it right at home, just like we did in Lessons 9 and 10. Your ultimate mission for this unit is a total shift in perspective. We are zooming way out from the 2011 Japan tsunami, and we're zooming right in on the unique hazard risks in your own backyard. You're taking the engineering process and those system models you learned for tsunamis, and you're going to apply those exact same scientific principles to a totally different natural hazard, one that could actually affect your own community.
I mean, a flooded street might be a much more realistic hazard for your specific region than a giant tsunami, right? So your job is to assess this kind of local risk. Just like we looked at that 100-year global tsunami map, you'll need to dig into historical data and hazard risk maps for your specific area. Does your town have a history of floods, tornadoes, maybe intense blizzards? You have to use that historical data to forecast your future risk.
Now, to make absolutely sure you get top marks on your final project, here is your communication checklist, pulled straight from your rubric. First up, you've got to use digital tools to analyze local historical hazard data. Second, use that data to predict the future risk and severity of the hazard. Third, you must identify your community stakeholder needs. Basically, who are you warning and what do they actually need to know? And lastly, and this is a big one, you must communicate clearly. Because a highly engineered warning system is completely useless if the people hearing it don't understand it. Your final product needs to thoughtfully pair visual symbols, images, and text, and keep it to everyday language so that everyone in your stakeholder group knows exactly what to do the second that alarm sounds.
So, I'm going to leave you with this final vital question as you head into your assessment. Which natural hazard threatens your community? And how will you communicate the plan? You've got the science down, you understand the engineering, and you know exactly how to read the data. Now it's time to put it all together and become the hazard communicator your community really needs. Good luck on your final project, and keep using science to make the world a safer place.